In this lesson, we're going to talk about derivatives and begin with defining a derivative. If you recall from the study of geometry, an important concept was the idea of a tangent line to a circle. This was a special line that intersected the circle at only a single point and was perpendicular or normal to the radial line at that point. The term normal, perpendicular both mean the same thing, so just wanted to point that out. Let's take a look at this. So here I have a circle and it's centered at point C, and I have point P on the circle and a tangent line graphed at P. And you can see that this point that's directly horizontal from point C, you can clearly see that that's meeting the radial line, which is the line that's connecting a point on the circle to the center, is 90 degrees to the tangent line. But even if I move this tangent line to a different position, so if I move point P around the circle, the tangent line still only intersects the circle at one point and stays normal or perpendicular to that radial line at every single point on the circle. And the question is, if it works that way for a circle, can we do this for any curve? Can we find some tangent line to any particular curve? And that's our goal in this particular section, trying to define a tangent to any curve on a graph. So let's take a look at a different app. This time one that's going to show us a tangent line at different points on any curve. And let's see if we can try and develop a definition for a tangent line to any other curve rather than just a circle. So the question here is, how do we go about defining a tangent line to any curve? If we look at the properties of tangents with respect to circles, well, first off, we have that it only touches the circle at one point. So I've got a point P on a graph, and I've given the tangent line, so we can see the tangent line. And the thing is, the requirement that it touch the graph only at a single point isn't necessarily a definition here, because let me move point P over to right here. Well, now not only does the line touch the graph at a particular point, there's also this other point down here where the graph is crossing the tangent line, so it isn't necessarily always going to cross a graph at a single point. So that doesn't quite hold as a definition. That it needs to be normal to a radial line, well, that actually works pretty well, but how do we define, how curved a graph is at a particular point? That's actually something that we do study later on in calculus, but for right now it's not something that we have the ability to look into. So another concept is possibly that it's a graph, that it's a line that never crosses the graph. So if you'll notice, on both sides of this particular graph, the tangent line is above the curve on both sides. So it's not crossing the graph. So another idea might be, okay, so it's a line that doesn't ever cross the graph. But if I come down here, at this particular point, this graph does cross the tangent line. So that's not necessarily always going to be the case either. What does tend to hold here is that at a very zoomed in level, all right, let me go back up here for instance. At a very zoomed in level, we have a line whose slope is very similar to the slope of the curve at that particular point. And if I really zoom in, you can see, the line, the tangent line and the curve are very good approximators for one another on a very zoomed in level. So this tangent line sort of linearizes the curve on a really small region around the curve. And so, around the point in question. And so that is one way that we can look at tangent lines. The slope of curves. That's going to be our approach here. So lines possess slope. That's one of their major aspects. And the curve tends to have a slope on a very small, very zoomed in region. And so that's why we're going to use the concept of slope to help us really define a tangent line, which later on we're going to call a derivative. So let's think about slope then. Okay. So slope is known as the measure of the direction of a line. And we've defined it back in earlier algebra courses. It's very simply, conceptually defined as rise over run. So the amount of distance you move in the y direction, up or down, that's your rise, compared to how much you're changing in the x direction, that's your left and right, so that's your run. In calculus, we will often call these quantities delta y and delta x. Delta y is just simply the change in your y variable, and delta x is the change in your x variable. And changes in those two variables can be measured simply by subtracting a start point from an end point. So if you have 2 points on a graph, you can find the slope between those points by taking the difference between their y coordinates divided by the difference between their x coordinates. But now suppose we have the curve of some function. We'd like to find the slope of the tangent line at some point P along the curve. I'm going to pull up an app so that I can show you in real time exactly how this process is working. But I have a description here which walks you through what I'm going to be doing in just a moment. So let me pull up that app. So I have the graph of a function, and it doesn't matter what function this is, it's going to work the same for any function. And on this function I have 2 points, P and Q. P we're going to leave in the same position, but Q I'm going to allow to move around. Ultimately what I want to do is determine what the slope of the tangent line is at point P. Now, if you want to determine the slope of a curve, you can always use slope formula. But if you want to find the slope at one point, the slope formula no longer works for you. So for instance, this point is at about 1 and 0.5. So if I have an x coordinate of 1 and a y coordinate of 0.5. If I want to find the slope at that particular point, the slope formula tells me to take the y coordinate of the first point minus the y coordinate of the second point divided by the x coordinate subtracted. Well, I end up with 0 over 0. So you can't directly calculate the slope of a curve at a particular point using the slope formula. However, this 0 over 0, if you'll recall from our limits, this is an indicator that there's probably some sort of algebraic reduction that we could do and actually come up with this value through the limiting process. And that's effectively what we're going to do. We're going to allow the value of Q, let the x value of Q get closer and closer to the x value of P. And as the x values of points P and Q get closer and closer, I get a better and better approximation to what the slope of the tangent line is. If I let it get extremely close and take a limit, I will get the actual slope of the tangent line. And that's effectively our process that we're going to do. We're going to learn to take the limit of a set of slopes. But before we get too far along, let's make sure we can really pin this process down mathematically, because ultimately you're going to need to do this stuff on your own in your homework. So let's make sure we can do each of the parts of this individually. Starting with calculating slopes of secant lines. Okay. Let's say we have a function f of x equals 2x squared minus 5. And I want to find the slope of the secant line between the values x equals 1 and x equals 2. Now, the slope of any line between 2 points comes from taking y2 minus y1 over x2 minus x1. I already have the two x values, and it doesn't really matter which one I call x1 and which one I call x2, as long as I'm consistent. But I do need to know the y values. But I can get the y values through the function itself. So let's say I call this x1. So then f evaluated at x1 would be 2 times negative 1 squared minus 5. And that would be negative 1 squared is positive 1, 2 times 1 is 1, so 2 minus 5, or negative 3. So that's the y coordinate associated with x1. So that's my y1. And similarly, y2, if I just plug into my function, and I'm kind of out of space to do that, so I'll just write it small here. F evaluated at 2, this would be 2 times 2 squared minus 5. So 2 squared is 4, 4 times 2 is 8, and then 8 minus 5 is 3. So that's my y2. Now that I have my y1 and y2, oh, I guess I should have specified that this would be x2. I can now calculate the slope between these points. And it doesn't much matter what order you put the slope, the x1 and y1 in, as long as you're consistent. You just have to make sure you get the negatives taken care of. So I called y2 was 3, and y1 was negative 3. x2 was 2, and x1 was negative 1. So I plugged my values in. Now I just need to be careful with the negatives. So 3 plus 3 over 2 plus 1, that is going to be 6 over 3. So I have a slope of 2 between these points. Now, very often, one thing that we need to do is, once we have a slope between 2 points, is we need to find a line that connects them. So let's make sure you know how to take a point and slope and come up with a line. The formula that you need to remember here is the point-slope form of a line. And that looks like y minus y1 equals m times x minus x1. It's essentially just the slope formula all again, but you only need a slope and 1 point for this to work. You don't need 2 points. Recall that the y values associated with negative 1, that was negative 3, and associated with 2, that was positive 3. Now, in order to come up with the equation of a line, I need my slope, and the slope we just found from calculating it through the slope formula, that was 2. I just need one of these 2 points. It doesn't matter which one. I think I'm going to go with the point negative 1, negative 3. I'll take this slope and this point, plug it into my formula. So it's y minus, and y1 is, whoops, negative 3. Sorry about that. And that's equal to my slope of 2 times x minus the x coordinate of this point, which is negative 1. Don't plug in both points you have to have a y and an x variable in the end in order to make the equation of a line. So you only plug in one of the 2 points, and it doesn't matter which one you choose. So this would become y plus 3 equals 2 times the quantity x plus 1, or y plus 3 equals 2x plus 2, and then subtracting 3 from both sides, I come up with y equals 2x minus 1. And that's the equation of the secant line between these 2 points. So of the function 2x squared minus 5, I have that graphed here in blue. And then in purple but dashed, I have my secant line, because this is the coordinate -1, -3. This is the coordinate 2, +3. And I've got the line graphed between those 2 points. I use the equation y equals 2x minus 1. Everything fits exactly as we would expect it to. So we've calculated the slope of the secant line between those 2 points. Okay, now just to shore up what happens if you try to calculate the secant line at a single point, let's try and do the slope of the secant line at x equals -1. Again, the y-coordinate associated with this is -3. So if I try and calculate the secant line at this particular point, y1 is -3, y2 is -3. Sorry, I said 2 as I was writing. And then x1 minus x2. All right, so at this point, what happens is I get -3 plus 3 divided by -1 plus 1, or 0 over 0. This value that is meaningless. It's indeterminate. So it could be undefined, or it could actually result in a value. But what happens with these slopes of tangent lines is it often does result in a value. We just have to come up with the means of determining what that value is, and that means is the limiting process. So what I'm going to do next is find the slope of the secant line between points P and Q for each point Q on my curve. X is given in the table, and then I'm going to use those answers to estimate a value of the slope of the tangent line. It sounds like a mouthful, but just watch along here. All right, so point P has the coordinates -1, -3. So this is still on my graph of f of x equals 2x squared minus 5. So point Q has the coordinates, well, x is indeterminate. We're going to let x be different values, and then we'll calculate the y value using f of x. Okay, so we could also say that point Q has the coordinates x comma 2 times whatever x is squared minus 5. And to speed things up, I'm going to first develop a function that will do this for me, and then use the calculator to help do this at multiple points and see what's happening with the slopes. All right, so the slope between any point on the curve Q would be y2, so the y coordinate from point Q, minus y1, so minus the y coordinate of point P, divided by the x coordinate of point Q, which is x, minus the x coordinate of point P. This is going to simplify a little bit. 2x squared minus 5 plus 3 over x plus 1, or 2x squared minus 2 over x plus 1. And you might recognize that that could algebraically reduce, but ignore that for the moment. We're going to just do this using the table method. So to calculate this limit using the table method, I'm going to use a table in the calculator just like we did from the limit section. So let me unveil my function here. In the numerator, it's 2x squared minus 2. And in the denominator, it's x plus 1. So notice I'm putting parentheses around the numerator and denominator because that long division bar there sort of implies that there's parentheses around those parts because there's multiple terms. All right, make sure my table is set up properly. That's great. And I'm going to start putting in values of x. So starting with negative 1.1. So this is a point that is close to negative 1, but it's not equal to negative 1. And the y value that I get there is negative 4.2. So I can calculate the slope between x equals negative 1 and x equals negative 1.1 because these are two different points. And I can get an answer. I can get closer and get another slope. It's a little bit closer as well, so negative 4.02. I can get even closer, negative 1.001. Still get an answer, negative 4.002. I could even get closer still, but I think we're close enough to where we can draw a conclusion here in terms of a limit. Those slopes are going to approach negative 4. So that effectively is the slope of our tangent line, the value that these slopes are approaching. One thing that I want to mention is if you actually put in negative 1, which looks like what it did in the cell above, it's just since I had so many zeros, it rounded it down to negative 1, so this one is just an error in how the calculator is showing it. But if I actually type in negative 1, then I get an error because it's getting that 0 over 0, just to point out to you. But the main bullet point here is that the slopes of these are approaching negative 4. Which is the slope of our tangent line. So the limit of the slope of a set of secant lines is the slope of a tangent line. Now, if we let x equals c be the value for which we would like to calculate the slope of the tangent line of some function f of x, we can generalize this process by evaluating the following limit. So it's the limit as x approaches c f of x minus f of c divided by x minus c. Notice the form of the slope formula. So this part right here, basically, without the limit, would give us the slope of secant lines. Here, with the limit, gives us the slope of tangent lines. So as you take the limit of a set of secants, that gives you the slope of a tangent. And this is known as our first definition of the derivative of a function at a point. So let's use this limit in order to calculate the slope of the tangent line of f of x equals 2x squared minus 5 at x equals negative 1. So just to point out, finding the value of a derivative and calculating the slope of a tangent line mean the exact same thing. We use that interchangeably in calculus. Now, here's what I need to do. So first off, we've mentioned it already, but we're going to need f of negative 1. So that's 2 times negative 1 squared minus 5, which ends up being negative 3. So we have that already. Now, the derivative will be found by taking as x approaches -1 of f of x minus f at -1 divided by x minus -1. So all I've done is I've taken my formula here for a derivative, and I've just let c be the value -1, which is the point in question. Okay, so next step, I need to expand some things out. So the limit as x goes to -1, f of x is the function 2x squared minus 5, and then we're going to subtract from that f of -1, which is -3, and divide that by x plus 1. All right, so if subtracting -3 is the same thing as adding +3, that would give me the limit as x approaches -1 of 2x squared minus 2 divided by x plus 1. Now, still, if I put in the value -1 to try and evaluate the limit at this point, I still end up with 0 over 0. But if you'll notice, the numerator has some things that will factor at this point, and that's the key to unlocking this. So I have a common factor of 2, which would factor out, and leave me with x squared minus 1. And then x squared minus 1 can factor into x plus 1 times x minus 1. So what happens now, this term, x plus 1, cancels out of the numerator and denominator, so that I get the limit as x approaches -1 of 2 times x minus 1, which I can plug in -1 at this point. It's 2 times -1 minus 1, which would be 2 times -2 or -4. So without using the table method, I was able to do that limit directly. And with these derivatives, you will always be able to do that. Okay, and just for additional practice, let's do this. Let's find the equation of the tangent line of f of x equals 2x squared minus 5 at x equals -1. So that just means taking the slope, which is -4, along with the coordinate -1, -3, which is a point that's on the curve, and plugging that into the point slope form of a line, which if you don't have that memorized, go ahead and lock it in, because that's going to get used quite a bit in calculus. So y minus the y coordinate of your point equals m times x minus the x coordinate of your point. So y plus 3 equals -4x, and so minus -1 is the same thing as plus 1, but I'm going to multiply everything through by -4, so this becomes -4x minus 4. And then if I subtract 3 from both sides, I get my final form, which is y equals -4x minus 7. And if you graph this, and I encourage you to do so on your calculator so that you get practice with graphing things on your calculator, but what you should see is the parabola, which is 2x squared minus 5, and the tangent line, -4x minus 7, touches the curve at the coordinate -1, -3, and it is a really good estimate for the slope of the curve at that particular point. So that's what our duty of a tangent line was. Here's another question that isn't common a lot of times in homework sections of calculus, but I'm bringing it up because I think it's an important thing to understand as well. So we mentioned with the definition of a tangent line to a circle, that it was normal or perpendicular to the radial line of the circle. Here, we don't have anything that is perpendicular to the curve or normal to the curve, but we can come up with something using our tangent line. So remember, normal is just another word for perpendicular, and perpendicular slopes, sorry. Perpendicular slopes. We learned early on in algebra that when two slopes are perpendicular to one another, that if you compare them, they have to be negative inverses of each other. So if you have the slope of a function at a particular point, you can get a slope that's perpendicular just by taking the negative inverse. So if I have a slope of -4 for a tangent line, then that means the slope that is perpendicular to that at the same point would be 1/4. Still using the same point on the curve. So the point on the curve that I'm interested in is still -1, -3. And I plug this into my line equation. So y minus -3 equals 1/4 times x minus -1. So y plus 3 equals 1/4 times x plus 1. Or y plus 3 equals 1/4 x plus 1/4. And then to subtract 3 from both sides, I'm going to have to combine some fractions. So an equivalent statement to subtracting 3 is subtracting 12/4, just getting that common denominator. So that gives me the line equation 1/4 x minus 11/4, which might look a little bit strange, but if I graph all of these on the same set of axes, the blue is the curve, and I've changed the scale on this a little bit so it looks different, but it's the same curve, and that's 2x squared minus 5. In purple, I have the tangent line. So the tangent line at that particular point, 1, -3, that's what it looks like. Then in green, I have the normal line. So the curve that is at a right angle to this tangent line, thus also being perpendicular to the, we could call it the radial element of the curve itself. So you can determine something like that just by making the slope of the tangent a negative inverse. Now, when you're doing homework, you have a lot of different ways of being asked the same kinds of questions. So I want to give you some equivalencies of terms that you run into pretty commonly in homework sections of calculus books. So the first group of equivalencies are going to be about secants. So if a problem asks you to find the slope of a secant line, obviously it wants you to use the slope formula to do that. So that's m equals y2 minus y1 over x2 minus x1. If it wants you to find an average rate of change or an average velocity. So the term average here is key. So average tells you you're doing stuff with secants, which is the slope formula. Or find delta y over delta x at x equals c. So delta y is y2 minus y1. Delta x is x2 minus x1. So it's really just telling you to plug directly into the slope formula. These are all the same, and just want you to use the slope formula to find an answer. However, if a problem asks you to do things like find the slope of a tangent line, well, the tangent line is related to secant lines, but you have to do a limit. So the limit as x approaches c, f of x minus f of c divided by x minus c. So you're doing the limit of slopes of secants for tangent lines. if it asks you to find instantaneous rates of change. So the key difference is instantaneous items, or instantaneous velocity for that matter. This is happening at a single point, a single instant in time. That means you need a tangent, to do this limit here. To calculate a derivative, the term derivative is the same thing as tangent. Find f prime of c. I haven't introduced the prime notation, but we will discover it as we move along. But for now, just know if you see that, it's talking about derivatives. dy dx. We haven't introduced this notation either, but I'm putting it here for completeness. Very common way of expressing a derivative. All of these are equivalent, and they want you to use the limit definition of a derivative to find the answer. Probably won't run into it much in this class, but if you're taking an economics course and you're doing anything marginally, so if you need to find the marginal cost, something like that, marginals are also derivatives of things. So just bonus material there for you. But lastly, if you're asked to find the equation of a line, whether it's a secant line, a tangent line, or a normal line, thing you have to do first is find the slope that you need, then a point that exists on the line, couple that with your point slope form of a line in order to turn it into the explicit equation, and there's your point slope form. And in the end, the equation of a line should always look like y equals mx plus b. So you always need to reduce it down to that form. Let's examine again the limit definition of a derivative, but approach it from a slightly different perspective. Instead of picking 2 points along a curve and allowing the second point to get closer and closer to the first, let's choose a distance from the original point and allow that distance to decrease to 0. This is what is known as the difference quotient when we get to it. First, let's visualize the concept so you understand what I'm saying using this app. I have a curve of a function, and I still have 2 points that I'm calculating secant lines between. P is still the point that I want to find the slope of the tangent line. But what I want to call your attention to right now is this new term that I've put in, delta x. Delta x is the distance between the x-coordinate on point P and the y-coordinate of point Q. So this, the x-coordinate of point Q. So this is technically the point x plus delta x. So the y-coordinate of P is the function evaluated at x. The y-coordinate of Q is the function evaluated at x plus this distance. Now what we're going to do is allow that distance to change and get smaller and smaller. So if the distance between these 2 points gets smaller and closer to 0, we're going to get a better approximation for the tangent line. So as I bring point Q closer in, notice how delta x is decreasing in value. So delta x is getting smaller and smaller and getting closer and closer to 0. And as it approaches 0, that's when we get the really good approximations for the tangent line. So we're just allowing the distance between these points to go to 0 rather than the coordinates, the x-coordinates approach each other. So the way that we notate this, first off, this notation here, the delta operator, it means the amount of change in a variable. So delta x means the change in x. So point P I had located at x comma f of x. Point Q I had located along the curve, which was a distance away from P. So wherever P was, plus some distance away, so x plus delta x. And then the y value then is the function itself evaluated at that point. So when we calculate the slope of a secant line, then we can calculate by taking y2, which would be the y coordinate associated with the point Q, minus y1, which is the y coordinate associated with point P, divided by x2, which is the x coordinate associated with point Q, minus x1, which is the x coordinate associated with point P. Notice that this x and this x cancel each other out, so that leaves me with, oops, I have to go back to blue. That leaves me with f of x plus delta x minus f of x all over delta x. And you should recall this from a previous section when we talked about the difference quotient. And the idea is this is effectively another way of expressing the slope of a secant line. So if we allow these slopes to, if we allow delta x to go to 0 and take a limit, then what we do is come up with slopes of tangent lines, which here I'm going to go ahead and introduce this prime notation. So f prime of x is the derivative of the function f. And so this gives us another way of calculating that derivative. Let's try it out. Essentially, you can use either form of this limit. You'll get the same answer both ways. Sometimes one has an advantage over the other. It doesn't much matter in the end. But let me show you how to use both so you can choose whichever you prefer. So what I want to do in this example is find the derivative of the function f of x at x equals 4. And the function itself is 2x minus 1. So the derivative we just saw is the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. So we have a couple of things that we need to figure out first before we can plug stuff in, because it's going to look like f prime evaluated at 4, because I want the limit point to be 4. I'm sorry, the point x is 4, so I need to replace all my x's over here with 4. So this would be f of 4 plus delta x minus f of 4 divided by delta x. So the first thing I should come up with is, let's do an easy one. Let's figure out what f of 4 is. That shouldn't be too bad. It would be 2 times 4 minus 1, which is 8 minus 1, or 7. So that's not so bad. The other one's a little bit trickier, but still isn't too bad. F of 4 plus delta x. So remember these functions. The x is really just this empty box, and it says whatever you put in the parentheses over here on the left-hand side goes in all the x's on the right-hand side of your function. So this will become 2 times 4 plus delta x minus 1. And since that's a sum of terms, make sure you put parentheses around it so that you don't lose that part. This would simplify into 8 plus 2 delta x minus 1, which would be 7 plus 2 delta x. Okay? So now, supposing I have enough space to do this in, the derivative evaluated at 4 is going to be the limit as delta x goes to 0 of f of 4 plus delta x, which I just found to be 7 plus 2 delta x, and minus f of 4, which I found to be 7. And it's really no coincidence that I have a positive 7 and negative 7 in the numerator. With these limits, you often have lots of terms that cancel out. So let's go ahead and cancel those. Positive 7, negative 7 cancel each other out. So this is now the limit as delta x goes to 0 of 2 delta x over delta x. And those delta x's cancel each other out, effectively leaving us with the limit of a constant. So the final answer is just the constant 2. Let's try one more of those, but a bit more complex. So f of x equals x squared plus 3 at x equals negative 2. So I want to find f prime at negative 2. So that's going to be the limit as delta x goes to 0. F of x plus delta x. So x is negative 2, so negative 2 plus delta x. Minus f of x, so minus f of negative 2, all over delta x. Now, it might be helpful to go off to the side and try and do these things individually, or you can do them in line. It doesn't really make a whole lot of difference. I think I'll go off to the side and do them over here. So let's see here. F of negative 2, that's going to be negative 2 squared plus 3, which is 4 plus 3, or 7. F of negative 2 plus delta x is going to be x squared, so negative 2 plus delta x squared plus 3. When I FOIL this out, you can use the foiling process, or you can use the faster formula. You're going to get the square of the first plus 2 times the first, which will make that negative, times the second. So 2 times negative 2 is negative 4, times delta x is negative 4 delta x, plus delta x squared, so the square of the second, plus 3. So that becomes 7 minus 4 delta x plus delta x squared. All right, so now I have the limit as delta x goes to 0. F of negative 2 plus delta x became 7 minus 4 delta x plus delta x squared. And f of negative 2 was 7. Now I have positive 7, negative 7, which cancel each other out. So that's the limit as delta x goes to 0. Negative 4 times delta x plus delta x squared all over delta x. This next part I'm going to do in a couple of steps because I want you to see how this works, because I find a lot of calculus students making this mistake. Yes, there are delta x's in the numerator and there is a delta x in the denominator. However, when you divide a polynomial by a monomial, every term in the polynomial has to be divided by that monomial. Another way of thinking about this is in the numerator, you have a common factor of delta x, which you can factor out of those two terms in the numerator. Then you have this factor of delta x in the denominator, which can cancel that factor out, which leaves you the limit as delta x goes to 0 of negative 4 plus delta x, which is negative 4, because when we let delta x go to 0, this term goes to 0, so we get an answer of negative 4. But the thing you want to be careful of there algebraically, I see students that want to do things like try and cancel the first delta x with the one in the denominator, leaving another delta x squared. In this case, you would get the same answer, but it's not correct, and it's not going to work in every single case. So learn to do it properly. Differentiability. Okay, so at this point, we've discussed a lot about derivatives, but we haven't yet really pinned down a great explanation about what a derivative does. I think the best explanation is that on a local level, the derivative gives us the slope of a line that best fits a curve. In that respect, we can say that the derivative linearizes a curve. If we look at a derivative at different points along a curve, I think you'll be able to see how this is true and that it only works on a small interval around the point. But for most points on a curve, the tangent line makes a decent approximation of that curve. So let's take a look at a function and some different points along that curve. All right. On this function, I have point P, and I have a tangent line around at point P that you can see following the point that I choose. At very small intervals around point P, so for instance from here to about right here, the tangent line is a pretty decent approximation for that curve. The graph itself is curved, but on a small local level, the tangent line does a pretty decent job of showing what line best fits that curve and gives me a good approximation on a small region around point P. And it depends on how curved that particular point of the function's graph is. The more curved it is, the less of an approximation it becomes. But it does a pretty decent job at doing that. Let me zoom out just a little bit and try and explain why that happens to be the case. So, for instance, if we have some other point Q on the curve, so I could give the point P a coordinate x, and the height of point P would be f of x. So if I take x and plug it into this function, I would get the height of the curve at that particular point. Now, the value delta or q, if I move a distance in the x direction and call this distance delta x, then this point where q is x plus delta x, which means the y coordinate of q is f of x plus delta x. If I just take that new x value, plug it into the function, that gives me the height of point q. So that point is exactly where q rests. The distance from here to here, this is delta y. And delta y is precisely the value f of x plus delta x minus f of x. So we can calculate the change in y based off of what the change in x is. But what I want to show you is how the derivative is a decent approximation to what delta y is. So if I take the derivative and evaluate it at x, then I get the slope of the curve at that particular point. So the slope of this line right here is my derivative function evaluated at x. And if I multiply that by some horizontal change, then all that's going to do is give me a value that is slightly above, or how far away that is from the current height. Let me show you. So this distance to this point from this horizontal level, I can find the height of that by taking f prime of x times delta x. Let me parse through exactly what is happening here. So we have the derivative of a function defined as a limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. Which means that if we take away the limit, the derivative is approximately equal to f of x plus delta x minus f of x all over delta x. Taking away the limit takes away our precision with this derivative, and it kind of switches us from using tangent lines to effectively secant lines, which were approximations. Okay, if I manipulate this, I could then say that f prime of x times delta x then is approximated, let me be careful there, not say equal, is approximately f of x plus delta x minus f of x, which is what we called delta y. So the true change from this point here to q is delta y. That's approximated by this change right here, f prime of x times delta x. So you can get an approximation to the height of the curve based off of your derivative. Just walking back through the steps that we just did, the derivative is defined as a limit, which means we can make it an approximation by taking away the limit, or rearranging those terms. We can write this in a form that tells us how delta y and the derivative times delta x relate. But then manipulating that a little bit, if we get f of x plus delta x by itself, then what that says is the function itself is approximately f of x plus f prime of x times delta x. And what that does is tells us about what happens to the function within small increments around a point of interest. It tells us how we can approximate the curve in that way with a line. So the slope of the tangent line, in effect, gives us a linear approximation to a curve. And that's one of the big takeaways from a derivative. So whether or not a function can possess a derivative or not. So a function is not differentiable at a point that is discontinuous or where its graph makes a sharp turn. So a couple of examples here. This graph would be continuous everywhere except for the asymptote. Because the asymptote is a point that the function is undefined, the limit doesn't exist there, it's a discontinuity, however you want to look at that, it would not have a tangent at that point. In this case would be -2. But any place you have a discontinuity, there would not be a tangent line there. And even if it was just a hole in the graph, which isn't as bad a discontinuity as an asymptote, because a hole in the graph is a removable discontinuity, whereas an asymptote is a non-removable discontinuity, the graph is discontinuous there, and therefore you wouldn't be able to find a tangent line at that particular point. Also, when the graph makes a sharp turn. So if the graph makes a sharp turn, you also can't uniquely define a tangent line, because what would happen is the secant lines coming this direction would all be sloped this way. The secant lines coming the other direction would all be sloped this way, and sometimes they might converge, sometimes they wouldn't, and it doesn't really lend us to uniquely defining a tangent. So that particular curve is continuous because the limit from the left at point 2 is the same thing as the limit from the right. So, and it's defined there. So it's continuous, it's just not differentiable. So the thing to take away here is continuity does not imply differentiability. Okay? But if it is discontinuous, it is not differentiable. Last up, derivatives as rates of change. So imagine that we have an object whose position is determined at any point in time by the function s of t, where t is measured in seconds. So it has an initial position at s of 0, So whatever you put 0 into your function, it gives you where it is located. At t equals 1, so 1 second later, it gives you the position where it's located, and so forth. So if you know two different points along its path, you can find the average rate of change between those 2 points. That's simply an average velocity, which is determined by doing a slope. So when you find the slope between these 2 points of position, you're going to get average velocity. And that should make sense to you, because if you take it to an idea of riding in a car, all right, and you travel 390 miles in 6.5 hours, then your average velocity, well, your starting position is at 0. So the average velocity here well, let's look at it this way. So whatever your starting position is, you went 390 miles from that. So the change in your position was 390, and the change in time is also measurable, so you did that in 6.5 hours. So that would be divided by 6.5. Now I have delta s over delta t, but that's no different really from delta y over delta x. It's the different name for variables. That's okay mathematically. If I put this into the calculator, oops, bring this over here so we can see it, then we can get that average velocity. So 390 divided by 6.5, that means we went an average of 60 miles per hour. So each hour that passed, we covered about 60 miles. You could have gone 61 the first, 59 the last, doesn't matter. Average velocity was 60 miles per hour. So the slopes of secant lines can be thought of as average velocities. But that establishes a link between the derivative and rates of change. Since the slope of a secant is an average rate of change, it stands to reason that the derivative, which is the slope of a tangent, is an instantaneous rate of change, which means the velocity at a single point. So we have the following rule about velocity that you should make sure you remember. That velocity is the first derivative of position. So if you want an instantaneous velocity at a particular point, you can find that by using this limit definition of a derivative.